Hello friends, continuing with our discussion on processing maps. Today I will like to take the or discuss some other different models. Okay, if you remember, we have already discussed dynamic materials model given by Y.V.R.K. Prasad, okay, and co-workers. So that we have seen in details. Okay, today we will see some other models which some other researchers have proposed, okay, and kind of some comparison between different models. So some work people have done on comparing these models and trying to correlate it with the microstructure. So you will see that a lot of different ideas people have come up to suggest a certain equation, okay, and in some cases these models are able to predict the unsafe or stable or unstable region for deformation processing, okay, and which are like validated with microstructure. In some cases some model will, or for example in some material some model will be more convenient or will be able to more predict in better way, okay. In some other material maybe some other model will be able to predict in a better way. So there is no final word on different models till now, okay. People are still trying to and still proposing new ways to plot the processing map or still proposing new models to understand the deformation behavior, okay. So as already we have discussed in DM model, okay, the stress is dependent on a strain rate, okay, and there is a power law relationship already we have seen, okay, a relationship like this. So you can see that this power law relationship, the M is supposed to be a constant, okay. So strain rate sensitivity is a constant here, okay. So they have assumed that strain rate sensitivity will remain constant in the strain rate range where they are trying to develop the model, and this kind of relationship is called power law behavior or power law relationship. However, if you are considering a large strain rate range, okay, then you will see that M does not remain constant. For a particular strain rate window, maybe you can take strain rate as constant, but if you keep changing the strain rate over a large window, you will see that the strain rate does not remain constant, and already I have told you that there is a power law breakdown also. That means the dependence on M will be the stress dependence on strain rate sensitivity or strain rate will be very small, dependence will be there, okay, sensitivity will be very low. So there will be a power law breakdown also, and M also keeps changing as a function of a strain rate, okay. So to take this into account, okay, the another model proposed by which is called as Murthy and Rao, okay, Narayan Murthy and Prasad Rao, they proposed another model which is usually called as modified DMM, okay, and they also proposed both the parameter, the efficiency, dissipation efficiency, that how efficiently material is able to dissipate the power through microstructural change rather than only through heat, okay, that is what we want. So they have proposed dissipation efficiency as well as the instability criteria, okay. So they have considered that the strain rate is going to change as a function of strain rate sensitivity. Sensitivity should come here, okay. Varying as a function of strain rate, okay. So that is why they have taken integral here, okay, as you can see here, okay, and this is eta Murthy and Rao, okay, where they have proposed an equation like this, okay. I am not going into detail of how they are coming up all these equations, okay, because in these lectures we do not have time to go into detail of each model, okay. But there are lot of research papers are available. So if you are interested, you can go to these research papers and see the derivation of these models, okay. Similarly, the instability criteria given by this model, okay, gives the instability like this. If you remember in case of Prasad and Rao, okay, where they have shown this as zeta, okay, and in this case the instability criteria is slightly different, okay, the 2m divided by eta. So, efficiency is coming there, and efficiency already we have seen they have calculated using a variable m, okay. So, that part is coming here, minus 1 should, if it is less than 0, then it has a instability, okay. So, one another variation to the same parameters, but looking in a different way, okay. So, basically they calculated J like this, total power minus G, okay, and which is equal to sigma epsilon dot minus 0 to epsilon dot sigma d epsilon dot. Through that they have calculated this efficiency, okay. There is another instability criterion, okay. This is proposed by Poletti and group, okay, and they said that means not to consider the strain rate sensitivity in the calculation, okay. So, they calculated directly from the J co-content, okay, the variation of J co-content as a function of strain rate, okay, and from there they calculated the instability parameter Kj, okay. So, another variation now looking in a different way, okay, to avoid strain rate sensitivity calculation there, okay. There is another model, okay, given by one more group, okay, which is usually we call it as a Giegel model, okay, and they use another some thermodynamic function which is called Lyapunov function, okay, and using that they propose two Lyapunov functions, okay, where now they are using efficiency. So, del efficiency by del ln epsilon dot, if it is less than 0, and they introduce another parameter here, okay, which is S parameter here, okay, and what the S parameter is? It is the temperature sensitivity of flow stress, okay, that how the flow stress is going to change as a function of temperature, okay. So, they have introduced another factor here which is temperature sensitivity of flow stress, and if you do some more jugglery with the mathematics, okay, you will come up with this particular parameter for instability, okay. So, one parameter is this, another parameter is this based on the temperature sensitivity. So, basically how the strain rate sensitivity is going to change as a function of temperature, and how efficiency is going to change as a function of strain rate. So, both temperature and strain rate dependence is taken okay, as a function of instability, okay. So, when it is less than 0, when efficiency change as a function of strain rate is less than 0, okay, that means it has a low efficiency, then it will be in unstable region, okay, or strain rate sensitivity as a function of temperature if it is less than 0, then again you will have instability, okay. So, another model for instability. Another model given by Malas and workers, okay, they replace eta with m in Giegel's criterion, okay. So, if you see here they have said eta. So, in the next one now you can see that instead of eta they have replaced it by m, okay. So, now it is strain rate sensitivity change as a function of strain rate if it is negative, okay. And also the one parameter which was introduced by Giegel, which was the sensitivity of flow stress to temperature, okay, that is still there. So, S parameter is still there, and this is another parameter which is like strain rate sensitivity as a function of strain rate, okay. So, you can try to see that these are variations of the parameters, okay, in different way they are looking at the problem in a different way and trying to come up with the instability criterion, okay. So, Giegel if you see and malas, if you see, more or less same, only the difference is that eta is replaced by m here, okay, in the first equation. There is another now a quite a change from the calculations which we doing, okay. Another one which is proposed by Semyatin and Jonas, okay. They have done lot of work on this. Now they have combined two material parameters here, okay. So till now we are only seeing the important material parameter is the strain rate sensitivity, and only we are looking at the variation of strain rate sensitivity change as a function of different variables, okay. They said that for any instability, when instability is there, okay, it also affects the strain hardening exponent, okay. So that is already we have seen in the room temperature deformation that whenever the strain rate hardening is not there, okay, or a material has a lower strain rate hardening parameter, then the instability can easily initiate and it can it can grow as a function of a strain, okay. So strain hardening, already we know this parameter strain hardening, okay, and strain rate hardening, or you can say strain rate sensitivity, both are same, okay. So gamma is your strain hardening coefficient, and m is coming as a strain rate sensitivity, okay. So they have introduced this parameter called alpha, okay, and whenever alpha is more than 5, okay, you have a instability, okay, and this particular value 5 they have found out for titanium alloys, okay. So still it is not a universally applicable phenomena or criterion, okay, because it has now this particular value has to be you have to determine for each material class, okay, that what is the value of alpha parameter is valid for that particular material, okay. So this is another instability criterion, okay. Now we would like to compare these criteria, okay, with different materials, in different materials, okay. I have taken the references, and the reference is always shown in the bottom part here, okay. So this is a work on beta titanium alloys, titanium 55531, okay, and 3 processing maps you can see here, okay. So eta, the efficiency is calculated by expression given by Murthy and Rao, okay, and in this case the instability is calculated by the parameter which is given by Polity, okay, if you remember Kj. This particular processing map eta is calculated by Prasad's calculation, the DMM model, okay, and of course zeta is the instability parameter, okay. And the third processing map, okay, eta is calculated again with Murthy and Rao, parameter efficiency is calculated by Murthy and Rao, the modified DMM, okay, and the instability is also calculated by the modified dynamic materials model, okay. So these 3 maps with different instability criterion, okay, is criteria is shown here, okay. So you can try to see that where the maximum efficiency you are getting. In case of DMM model, you are getting somewhere here and one here, and this area is the unstable area, that is the lower temperature higher strain rate. With instability criteria given by Polity, okay, you can see the unstable regions are here, okay, and the high efficiency regions are somewhere here, okay, and somewhere here, okay, and one is given here also. And in case of Murthy and Rao, efficiency is again Murthy and Rao, and instability is also from their model, okay. Again the of course the efficiency will be same, because in both the cases the efficiency parameter is taken as same, but you can see the instability is over a very wide range in this case, okay. Almost all the strain rates, okay, above 10 to the power minus 2, okay, it is showing instability, okay. So all the strain rate above this for all the temperatures, whereas in this case you are looking at certain pockets. And now they have done of course microstructural analysis. Okay. By doing a microstructural analysis, they have also plotted a deformation mechanism map kind of. Okay. So, you can see lower temperature, higher strain rate. Higher strain rate already we know that there is a lot of chances of adiabatic heating. Okay. So, you see that there is a adiabatic flow, that is the flow due to adiabatic heating. Okay. Somewhere here you have deformation bends and CDRX also, continuous dynamic recrystallization. This is the dynamic recovery in the beta field. Okay. This is your beta transist temperature, and this is your dynamic recovery in the beta field plus geometric dynamic recrystallization. Okay. And the subgrain size they have shown to increase in this direction. That means going towards higher temperature and lower strain rates. Okay. So, subgrain size is increasing because temperature is high, so more chance, and strain rates are low. So, more chances of subgrain size will tend to increase. Okay. And these are all done through this microstructural analysis here, where you have continuous dynamic recrystallization, deformation bands and so on. Okay. And looking at it, if you compare, maybe this DMM model is able to predict instability in this region. Okay. The top region here matching with that. Okay. Some part of this also is matching somewhere here. Okay. Whereas if you see the modified DMM, that is showing instability for a large range here. Okay. Which we are not able to see here. So, from this you can say that this dynamic materials model, the modified dynamic materials model is more conservative than other models. Okay. And if you see higher efficiency, of course, we are able to see dynamic recrystallization in this area where you have higher efficiency in all the cases. Okay. So, efficiency wise more or less both maps, whether we are creating with DMM or modified DMM, they are able to predict those areas where you are seeing dynamic recovery and dynamic recrystallization. Okay. Another work, another comparison in ultra high strength stainless steels. Okay. The models which are used are Prasad's. Okay. It is also called as Kumar and Prasad's. Okay. And one is by Malas. Okay. Already we have discussed that. Okay. And they have taken it as Alexander and Malas. Okay. Different groups have proposed this. Okay. So, they are showing instability criteria from Prasad's work, the DMM model, which is shown with red hatching here. Okay. And also with the Malas instability criteria, which is shown with blue hatching. Okay. And again then they must have done microstructural analysis at different conditions. Okay. And those conditions are shown on in the right one, this particular micrograph. Okay. So, these areas are the black, the square black field are the ones which are showing the dynamic recovery. So, this is the area where you have dynamic recovery. Okay. Then you have dynamic recrystallization. So, one area here you can have show as dynamic recrystallization. Okay. Then you have this area as okay, full DRX. Okay. And then this one you see as grain growth. Okay. So, if you compare with the instability criteria, and both they are not able to show the same instability criteria here. Okay. On instability conditions here, because you are seeing either dynamic recrystallization or dynamic recovery in this case. Okay. And of course, at high temperature you are also seeing the grain growth, which we saw in case of work by Poleti also, that the earlier work, that the subgrain size is increasing as you are going to lower strain rate, higher temperature. So, again here we are at lower strain rate, higher temperature. So, here you see grain growth. Okay. But more or less in this case the instability regions are not at least whatever they are reporting and whatever they are showing, okay, it is not being related with the microstructural analysis, okay, because both dynamic recovery and dynamic recrystallization we consider it as a safe deformation region, okay. So, we do not see that kind of instability here, okay. Another work on titanium alloy again, okay, and they have compared Murthy and Rao's model, DMM model of course, Prasad's model, okay, and Malas model, okay. And what they have also done here, that all these instability regions were plotted at different strain levels, okay. So, the strain levels are from 0.1 to 0.7, okay, at the interval of 0.1, okay. So, you can see lot of overlapping maps are there, okay, and as the overlapping is increasing it is becoming darker and darker, okay. That means the instability is either reducing or increasing as a function of strain, okay. So, that is what they are trying to show. So, if you see the DMM model, okay, the instability is starting from a lower strain rate, okay, and then going like some kind of diagonally towards the higher strain rate as a function of temperature, okay. So, at lower temperature, at lower strain rate also you have instability, and then it is going towards the, as you are going toward higher temperature, the instability is shifting towards higher strain rates, okay. If you see the Murthy and Rao model also, okay, again the behavior is more or less same, okay, maybe because both are based on strain rate sensitivity calculation, okay. So, you can see that again the behavior is like this, whereas for model given by Malas, okay, who considered also the effect of temperature on flow stress, okay, their model more or less all the boundaries are kind of covered with the unstable region, okay, and the central part is shown as the safe region, okay. And of course, again they have also done a microstructural analysis, okay, where they are showing different zones, okay. So, here low temperature, high strain rates, you will have crack initiation or cracking in the material, okay. Again low temperature, high strain rate, you have adiabatic shear band formation area, okay. Then you have at lower strain rate, okay, as you go towards higher temperature you have spheroidization. So, already we have discussed that spheroidization is also a safe region to operate, okay. It is a high efficiency, it should be related to the high efficiency region, okay. And basically your acicular type of structure gets spheroidized, you becomes globular, okay. So, like dynamic recrystallization, and as you go I think beta, this must be the beta transverse temperature. So, you have dynamic recrystallization in the beta phase, okay, and in this particular zone you have beta instability, okay. So, if you see more or less both DMM and modified DMM model of Murthy and Rao, okay, they both are able to predict this instability very nicely. Of course, they are not able to predict the instability in the upper region, that is the lower temperature and highest strain rate, okay, where in the microstructure it is showing cracking, okay. If you see the Malas model, of course, it is not able to predict the instability correctly, okay, because it is showing, of course, the cracking where the crack formation is taking place and which could not be predicted by both DMM and MDMM, that one could be predicted by the Malas model, okay. But the high instability in this region is not corroborated with the microstructural analysis, okay. So, you can see that different models sometime are able to predict some features, may not be other features, okay. In some cases they are conservative, in some other cases they may not be conservative, okay, and it all depends on how the material behavior is there. how the strain rate sensitivity is there, how the flow sensitivity is there to the temperature, to the strain rate. Okay. So, all these parameter, the material parameter kind of affects the the generation of the processing map, and every time any processing map when we generate, it has to be validated by microstructural analysis, okay, to confirm whether we are able to get the same efficiency instability in the microstructure also. Okay. This is some of our work. This is again PhD thesis of one of the student, Kuldeep Saxena. Okay. So, in our work we have compared in the zirconium niobium alloys. Okay. So, the alpha parameter given by Jonas and Semyatin, okay, and of course, modified DMM by Murthy and Rao, and DMM model by Prasad et al. Okay. That is what we have taken, and you can also see, as we have seen in case of earlier work also, that the modified DMM is more conservative here. Okay. Again showing very high instability in the all the strain rate above 10 to the power minus 1. Okay. If you compare the DMM model with the alpha parameter, both are able to predict instability in the lower temperature region and higher strain rate. Okay. So, that is clear in both. Okay. However, in DMM model there is another one instability region is shown at lower strain rate, okay, and also lower temperature. Okay. And more or less the high efficiency regions are these and these. Okay. So, that is also can be seen in the modified DMM model. Okay. So, again different approaches, different ways of plotting the processing map. Okay. Again we can also try to do the microstructure analysis. I will show you that. Okay. For example, this is another work on 2.5 niobium, zirconium 2.5 niobium. Okay. Again the comparison is there between the DMM model, modified DMM model, and alpha parameter at two different strain level. Again it is plotted as we have seen in previous works also. As you go from 0.3 to 0.6, you can see there are some changes in the instability regions as well as the efficiency region. As you can see at lower strain, okay, only instability is here, but as you go to higher strain, the instability is coming in these regions. Okay. Efficiency, if you see, you are getting high efficiency in these regions. Okay. And similarly at low strains also the efficiency is high in these regions. Okay. Again if we compare with the modified dynamic materials model given by Murthy and Rao, okay, the instability is shown in the middle part. Okay. And as you go to high strain, all the strain rates above 10 to the power minus 1, you can see the instability. In alpha parameter, the instability is extending. At low strain it is in a small window, but at high strain it is extending for all the strain rate range. Okay. Now, if you compare with the microstructures, okay, we are taking this DMM model here. Okay. And from there we are taking the sample where we have high efficiency, where we have instability. Okay. So, the red dots are showing you the instability is also observed in the microstructure, whereas the yellow dots are showing you that there are no instability in the microstructures. So, for example, from the model it says that there should be an instability at 900 degrees Celsius and strain rate of 10 to the power 1, okay, but we do not see any instability at that condition. But other condition we are able to get instability as predicted by the processing map. Okay. And those are you can see the processing conditions are also shown here. Okay. So, for example, you have voids formation here. Okay. Also some type of cracking at higher strain rates. Okay. At higher strain rate I can see cracking here also, whereas you can see adiabatic shear bend formation at strain rate of 1, okay, and at lower strain rates, okay, you can see the microstructures are actually the microstructures are not very clear. The reason is that in zirconium niobium alloy there is a martensitic transformation when you quench the material, okay. So, because these are deformed at higher temperatures, okay, in some cases it has gone into beta phase, okay. So, when you quench from beta phase there will be a martensitic transformation and that kind of covers the actual microstructure which might have been there during the deformation process, okay. But at least I cannot see instabilities in these microstructure, whereas the microstructure from the unstable region of the processing map I can see that there are few instabilities are there, okay. This is the comparative table for that previous slide, okay, that where you can have unstable region and so on, okay, and which particular model is able to predict correctly, okay. So, that is shown in the last column here, okay, whether DMM is the one which is able to predict this particular region. In another region DMM, all the 3 parameters or models are able to predict the partial recrystallization at this particular processing condition, okay. So, like that it is all kind of summarized in a table, okay, and the work is taken from a paper, okay, our own work is there. So, if you want some details you can go to this paper also, and for other models and other work also I have shown you the source from by which I have taken it, okay. And if you actually see the work which is being carried out in high temperature deformation or thermomechanical deformation, huge amount of work on processing map, constitutive equation development for each class of materials, okay, and comparison of different models, okay, comparison of different constitutive equations. So, there is a huge amount of work which is there, okay. So, I cannot of course take all this in a small lecture like this, okay. So, I would encourage, if you are interested, to go and look for these publications, okay, and this lecture can serve as a introductory lecture for you, okay. So, with that thank you for your attention.